I'm Anil Kumar, and in this video we will discuss displacement time graph, and we'll also see how to relate displacement, velocity and acceleration with the help of higher order derivatives, right? So what we're trying to see is we are looking at three different functions. The first one for us is displacement. So let me write them down. Displacement. The second one is velocity, and the third one is acceleration. In general, we'll say S of t as displacement, V of t as velocity, and A of t as acceleration, right? Now, as you know, velocity is rate of change of displacement. Since velocity is rate of change of displacement, we can say V of t is equals to S dash of t, right? And acceleration is rate of change of velocity, so we could write A of t is derivative of or rate of change of velocity, right? Now, since velocity is rate of change of displacement, acceleration could be written as second derivative of displacement, right? So that second derivative is what we are saying higher order derivative. So I hope you understand the concept. So in this particular chapter, we are working with not just first derivative, we are working with second or more also, right? So what we observe is that acceleration is second derivative of displacement, right? So that gives rise to higher order derivative. So that is one part which we are going to discuss. The second part which we are going to discuss is how their graphs are related. So what I will do here is I'll kind of sketch one graph. Let me just sketch one graph and then we'll work more on that particular graph. Let us say that we have a displacement. There's the body which is moving, and that's the motion of a body along a straight line. So here we are showing time on the x-axis, and this graph is for displacement. Let me write S of t. Clearly, we observe that the object is moving, let us say moving towards right, that is positive for us, and at this point it turns. So at this point it turns. If I draw a tangent here, that tangent is going to be horizontal. Similarly, a tangent here will be horizontal. So these are my turning points, right? So we have turning points here. And these turning points also reflects you change in direction, right? So these turning points gives you change in direction. So a body was moving forward, it starts moving backwards after this point, right? Change in direction. Now you'll also observe that on the left side, if we draw a tangent, it will be positive slope. On the right side, the tangent has negative slope. Tangent is the velocity. So at this point, what do we observe? We observe that the velocity v of t equals to 0 at these points. So let me call these points as point A as t equals to, let us say, A, and this is at t equals to B. So we can say that at t equals to A or at t equals to B, the velocity is 0, since these are the turning points and the slope of the tangent is 0. I hope you get the point, right? On the other side, what you see is if you check from 0 to A, so if time is between 0 to A, then if I draw a tangent, then we observe that velocity t is greater than 0. Is that okay? But if we consider the time between A to B, at that time velocity is negative, since the tangent drawn here will have negative slope. since the tangent has negative slope, velocity is negative from time A to B, right? However, after B, so if t is greater than b, then again it is positive slope, right? So the velocity is greater, correct? So if you have to sketch a graph of velocity from this displacement, you can say it is very high velocity to start with, it decreases, becomes 0, and then negative, right? So it is negative kind of here. So it could be kind of like this. So if you draw a graph, we are expecting this kind of a graph for velocity. Do you see that? So that is the kind of velocity graph. So, that is what you get. So for basic understanding, I hope we'll take up equations and concrete values later, but I think this video gives you the basic concept. Now let's move on to acceleration from here, right? Now acceleration is change in velocity. Is it okay? So you see, at this point the velocity is 0. So let's call this point as, let us say, c, right? C. So at t equals to c, we find that, now let me write acceleration on the right side. Acceleration is equals to 0 at c. Do you see? Because we have a horizontal tangent at t equals to c. If I draw tangents on the left and the right side of this parabola, you see a negative slope here. So if I have acceleration which is negative on this side, positive on the other side, this kind of looks like a linear. So if I sketch the graph for the tangent, then I may have a graph which could be kind of like this. Do you see that? Kind of like this. So what you observe here is that the acceleration a of t is less than 0 when t is between, if t is greater than 0 and less than c, in that case acceleration is negative. However, acceleration is positive after c, right? So what we observe here is that, let me write down here, a of t, acceleration, is greater than 0 when t is greater than c. Do you see that? So that is what we observe from here. So acceleration is the second derivative of displacement and is the first derivative of velocity. So you can actually sketch the graph of acceleration from the graph of velocity, and you can sketch the graph of velocity from the graph of displacement. So that's the idea which I'm going to float with you or share with you in this particular video, and I hope that point is well taken. So in the next graph we will take up concrete values and then work out. But here I think the concept that the turning points on displacement indicate that the velocity changes. Turning points indicate that the velocity is 0 at the turning point. Before and after, velocity can change. Turning points on the velocity indicates that the acceleration is 0 at that point, and it could be positive or negative on either side of that 0, right? So we'll analyze these things in the coming videos and explore further higher order derivatives. I hope that helps. Thank you and all the best.